We've made the claim a few different times that fiber channel and Ethernet are like oil and water, they don't get along. And that is true. However, we can embed fiber channel inside of Ethernet frames if we deploy a strict set of protocols in order to support it. So unlike iSCSI, where we can just send SCSI messages inside TCP/IP and throw it across any old switch, fiber channel over Ethernet is a little bit of a different animal. We're going to have to make sure that we specifically support different ways to ensure that we, remember, deploy a lossless fabric to represent how fiber channel should function. Let's dive in and see this in action. Once upon a time, we had two different voice networks. We had the traditional analog network, and this would be old PBXs, and it would be the old Cat3 wiring. And then we had the data world. In the data world, we had TCP/IP, and we had Cat5 cabling at the time. And Cisco came along in all of this and said, hey, couldn't we merge this world into this world? Couldn't we get voice over IP working such that we don't need to manage two distinct networks? Well, some time ago, somebody looked at the fiber channel world and said the exact same thing. We have dedicated fiber channel switches. We have MDS line, for example. We're deploying host bus adapters. And this is one side of the world, but then on the other side of the world, we have Ethernet switches. And we have 10 gig and maybe even 40 gig. And the question is, can we merge fiber channel into this Ethernet world? And even though the parallels are strong, the challenge here was pretty significant because remember, fiber channel requires a lossless fabric. And as we discussed many times, Ethernet is far from lossless. It's considered a lossy protocol. And so this was quite a task to be able to say, hey, could we deploy a lossless protocol inside of Ethernet? And ultimately the answer is yes, we are able to do this, but let's think through how we could possibly go about accomplishing this. And so when we think about it from an Ethernet perspective, if we have two different Ethernet switches talking to one another, is there a way, as we're just throwing all kinds of traffic out here, is there a way for this switch to say, hey, you know what? Stop. This is my attempt at an octagon-based stop sign there. Stop sending me traffic because my buffers are overloaded. And if you take a moment to really search deep into the back of your mind, you might remember having deployed something called flow control at some point in your career. Now, whether you actually have this experience or not, we can understand that flow control is an option that Ethernet has to say, hey, stop sending me traffic. I can't handle any more. This is a little bit different than how fiber channel does it. We recall that fiber channel is actually going to have two different switches, and I tell this switch, hey, this is how many buffer-to-buffer credits you get, and so this switch actually tracks and stops itself if it needs to give the upstream switch a break. However, the end goal is roughly the same. If my buffers are completely full on this switch, then the downstream switch is going to stop sending me traffic, and therefore I stop dropping Ethernet frames. So this is similar, however, there is another problem with this, and that is that if I'm going to send something across Ethernet, well, there could be not only fiber channel traffic coming into the switch, but also other Ethernet traffic. Maybe it's data traffic, and maybe they're both going across this same link. So now I have a lot of concerns. I have these concerns of contention. I have my data traffic competing with fiber channel on a single link. And furthermore, this concept of stopping the traffic, imagine I'm on an 8-lane highway and there's a pothole in one little lane and they decide to close the entire highway just because there's one little pothole that showed up in one of the lanes. If the fiber channel traffic needs to stop and I stop my entire Ethernet segment, well, that's going to be a big problem for all the other traffic that's trying to make it across that link. This is why even with a concept like fiber channel over Ethernet, we cannot simply throw FCOE traffic across any old TCP/IP switch. Instead, we're going to need a dedicated set of protocols to solve some of these problems. So let's get into these. The first protocol we're going to talk about is called priority flow control. Now, hopefully you were paying attention because I just told you about flow control. Now we're talking about a protocol called priority flow control, otherwise known as PFC. So as we can imagine, there's probably going to be a relationship here. And indeed there is. Priority flow control is going to allow us to send those pause frames on a per COS basis. What that means is I can now say, hey, stop sending me any traffic that's marked with, let's say, class of service 3. Now, in a previous skill, we had talked about how fiber channel over Ethernet defaults to COS 3, so maybe it is 3 in your environment, maybe it's a different COS tag, but either way, priority flow control allows me to say, hey, only stop sending fiber channel traffic, and I use class of service in order to identify that. This gives me the idea that I'm trying to get to, which is lossless Ethernet. However, it's lossless Ethernet only for the fiber channel traffic. It's not going to be lossless for anything else on the network. Priority flow control was actually standardized. This is not a Cisco concept. It was ratified as 802.1 QBB. And so I don't have to speak, for example, from one Cisco switch to another Cisco switch. Fiber channel over Ethernet is standardized. I can communicate between Cisco devices and third parties as well. So we've got options there because everything is standardized. Now next, what about this idea over here that I might have data and fiber channel traffic trying to traverse the same link? How do I deal with contention? Well, fortunately for us, Cisco has all kinds of rules about quality of service in the network. But I just mentioned that we might be communicating through third-party devices. My upstream device might not be a Cisco device. I could be connecting UCS to a different non-Cisco branded switch and needing to run FCOE that way. As a result, I can't rely on Cisco's QoS mechanisms. Instead, we needed a new standard, and that standard is known as Enhanced Transmission Selection, otherwise known as ETS. Enhanced Transmission Selection is all about quality of service. We want to make sure that FCOE is able to get as much bandwidth on the link as possible. And again, this needed to be standardized. This couldn't just be, this is how Cisco does QoS, and therefore everyone should just do the same thing. We needed a standardized way of doing it, and as such, it was standardized as 802.1 QAZ. ETS is essentially going to allow Fiber Channel over Ethernet to be able to reserve a certain amount of bandwidth. FCOE requires a lot of bandwidth. We've talked about this, the concept of storing a lot of SCSI messages inside of payloads, and on the TCP side, we want to use jumbo frames, for example. Now, FCOE, the minimum amount of bandwidth we can dedicate to it is 10 gig. It can't go as low as 1 gig like iSCSI can. However, it can continue to go up. We can use 40 gig, 100 gig, etc. But the idea here is regardless of the underlying bandwidth of the link, we need to be able to make sure that we get ours, so to speak. We get the amount of bandwidth that we require for our FCOE traffic. So with these two protocols, we have solved our problems. We know that we can send stop messages to create a lossless fabric. We can use ETS to ensure we get the amount of bandwidth that we need. And both of these, PFC and ETS, are going to be required in order to run FCOE, which actually gives us a new problem. And that is, how do I know for sure that my switches upstream that I'm connecting to are compatible with FCOE? How do I know that they support the required protocols? Well, that introduces a third protocol into the mix. We call this the Data Center Bridging Exchange. Now, the acronym for this is a little bit funny. It's actually DCBX, where the X stands for exchange. This is actually standardized as part of 802.1 QAZ, and it's a way for switches to exchange compatibilities. Again, I'm going to connect my switch upstream to this switch, and I want to run FCOE. This switch needs to know that, hey, I can actually run priority flow control. I need to know that it can run ETS. And therefore, I use DCBX to, right when I first connect, to find out what your switch is capable of running. These messages that are exchanged are going to leverage LLDP, known as the Link Layer Discovery Protocol. LLDP is going to allow us to carry this messaging information across via DCBX. However, that also means that LLDP is going to be required in order to get FCOE online. So if I'm having any problems in my data center getting FCOE to work, I might want to check to make sure that LLDP is enabled before diving too deep into troubleshooting. So we accomplished the mission we set out to do, which is to get Ethernet to support fiber channel frames. Now, it came at a cost because we can't simply send fiber channel across any old Ethernet switch. It needs to be switches that support these protocols. So the first protocol we looked at was priority flow control. PFC is going to use those Ethernet pause frames to tell the downstream switch that, hey, I can't have any more frames coming in or I will end up dropping them. And priority flow control specifically allows me to send that pause frame on a per COS basis. So I can target the fiber channel over Ethernet tag and tell the downstream switch to not send any frames that have that COS tag. Now, Enhanced Transmission Selection, ETS, is going to give us some of those strict QoS requirements that Cisco's really good at deploying, but not every vendor is. And again, plus beyond the whether you're good or bad or not, the industry needed a standardized way of requesting bandwidth. And so the way we do that is with ETS, and both PFC and ETS will work together in order to get our links online. But all that said, we need a way to exchange our capabilities with our switches, and that would be the Data Center Bridging Exchange, or DCBX. The DCBX is going to allow my switches to talk to each other and say, hey, can you support PFC and ETS and such? And we're going to leverage LLDP messaging in order to do that. I hope this has been informative for you, and I'd like to thank you for viewing.